Alright, Assalamu alaikum. I hope you are doing really well. So, our today's lecture is all about the determinants. So, in the next few lectures, we'll be learning about determinants, eigenvalues, and eigenvectors, which are a big chunk of the linear algebra. Alright. So, I think you all have an initial idea of the determinants. So, our today's lecture is, if I'm not wrong, is lecture 15. I'm sorry. Okay. So lecture 15. In this lecture, we'll be learning about the properties of the determinants. Alright. And to know about the determinants, so what a determinant is, you have to you need to recall the idea of linear transformation. So what is a linear transformation? So Uh, so what was the tool of the linear transformation? The tool of the linear transformation was the matrices, right? So this sort of 2 by 2 matrices or 3 by 3 matrices actually was doing the task of linear transformation. And what generally linear transformation does is sometimes it stretches things out and sometimes it squeezes the things in, right? So determinant is a tool to measure exactly how much your things being stretched out or squished in. Alright. For example, think about this particular matrix. Now this one let's take an easier example. Alright. So for example, you have a matrix like this 3002. Alright. So we have two columns in this matrix which are 30 and 02. So it can be divided into two columns which are 30 and 02. So this 30 column, it actually scales the I cap by a factor of 3, right? And this 02 column, this actually scales the J cap by a factor of, as you can see, 2, right? How? So let's say you have a vector, let's say that is 1 1. All right. So um, if you multiply this 1 1 vector with this particular matrix, if you multiply this particular vector with this matrix, then you'll have a linear transformation something like this. So in 1 1 you have you are in here. So after the linear transformation, after the uh, multiplication of the matrix, so the linear transformation, let's say LT, your I cap. So this part will go to 1, 2, 3 here, and your J cap will go to here, 0, 2. So you'll have you have a vector. So this was your 1 1 vector. So after multiplying with that particular matrix, you'll come here in 3 2, right? So as you can see, the area the area of the vector has been stretched out by multiplying with that particular matrix. So you're already familiar with this idea, right? You're already familiar with this idea of a linear transformation with matrices, right? So if you think about this particular area, the linearly transformed area, after multiplying with this matrix, you can say that this is a rectangle. Got. So for the previous rectangle, it has a length of 1 and uh, the width of 1, right? So the area was 1, and in this case the length is 3 and the width is 2, right? So in this case the area, so all right, so this, let's say this is um, area, and in this case the area is in fact 3 into 2 is 6. So we can say that this matrix 3 0 2 0 2, this matrix 3 0 0 2 has scaled the area of that particular vector by a factor of 6, right? By a factor of 6. So this very special factor, the factor by which linear transformation changes any area, is called the determinants, right? So the determinant of this particular matrix is 6. That means if you multiply any vector with this particular matrix, the area of that particular vector will be stretched out by a factor of 6. That's why the um, determinant of this particular matrix is 6, right? Now for example, let's say some determinants uh, of some matrices are, um, let's say the determinant of this matrix is minus 1 1 and minus 1 minus 1. The determinant of this particular matrix is 2, because if you multiply any vector by this particular matrix, then the result will be the that vector that you have multiplied with this matrix, the area of that vector will be stretched out by a factor of 2. That's why the determinant is 2, right? And what about this one, the determinant of this matrix? So we will know by the end of this class that how you can actually measure the determinant of a particular matrix. Alright, so the determinant of this particular matrix 0.5 and 0.5 is in fact, sorry, the first bracket here. So the determinant of this particular matrix would be half, right? So what is the meaning? Like uh, what is the underlying meaning of the determinant of this particular matrix is being half? So the idea is if you multiply any vector by this particular matrix, the area of that particular vector that you have multiplied with this matrix would be squished into half, right? So the area would be decreased, right? So this is the idea of the determinant. Now there are two exceptional cases where the determinant can be a 0 and the determinant can be a negative number, right? So what do you mean by a determinant being 0? For this example, let's say for in this example, the determinant of this particular matrix is in fact 0. Why? Can you tell me why? So if you look at the um, columns of this matrix, we can say that the second column is linearly dependent on the first column. So the linear transformation done by this particular matrix would be squishing into a straight line, right? So if you multiply a plane, let's say a plane, if you multiply a plane with this particular matrix, the plane would be squished into a straight line, right? Sometimes the um, planes or a straight line are squished into a single point. So in those cases, whenever the area is squished into a straight line or a single point, it occupies no area, right? So if your plane, let's say this is your plane, this is transformed into a straight line. So the area becomes zero in this case, right? So after the linear transformation, the area becomes zero. So in these cases, the determinant is zero, right? And um, now the last example of um, of the different values of the determinant can be a negative example, right? So what do you mean by a determinant being zero, right? So, as you can guess, I think I already talked about this in our classes, in the physical classes, that this has to do with the idea of orientation. All right, all right. For an example, let's say you have this matrix, determinant of um, 2 minus 1, 1 minus 3. So the determinant of this particular matrix is a negative 5. Now what do you mean by a determinant being a negative 5? Alright. So as I told you that it has to do something with the orientation. Right? So whenever the orientation of space is inverted, the determinant will be negative. So for a normal case, for a normal case, let's say this is a 2D coordinate and this is your I cap and this is your j cap, right? So as you can see, the from the I cap to j cap you have to make uh, an anti-clockwise rotation, right? So the I cap is in the right side of the j cap, right? So from to go to the j cap from the I cap you have to make an anti-clockwise rotation, right? So let's say after the linear transformation um or multiplying, after the linear transformation means after multiplying with a particular matrix you have uh, you have a particular orientation like this. So your space becomes like this and here comes your I cap. So this is L I cap means the transformed I cap and L J cap means the transformed J cap. Alright. So as you can see here, from to go from I cap to J cap, you have to make a clockwise rotation, right? So the orientation of this space has inverted in this case after the linear transformation, right? So let's say you have a vector 1 1 and after multiplying with this particular matrix is your space becomes like this, right? So in this case the space is inverted, right? So whenever your space the orientation of your space is inverted, your determinant will be negative, right? So in this case your determinant is a negative 5, right? So this was all about the determinants in 2D spaces. So what about three dimensions? So in 2D, I mean the examples that we have seen so far, in 2D the determinants work with the area, right? That means how much the area has been stretched out or squished in. In 3D, on the other hand, it works with the volume. It works with the idea of volume, right? So the determinants in 3D tells you how much volume is scared. All right. So it is difficult to draw the 3D space there. So let's try. So mm, let's say this is the 3D coordinates, and you have a cube. You have a cube like this. Let's say this is your I cap, J cap, K cap. So let's say after, so this is your initial positions uh, of your vectors. Okay. Now after linear transformation, let's say you come to uh, this. Okay, I have some pictures, so let's see if we can actually import those pictures here. All right, so uh, it actually shows how you can actually uh, work with the idea of determinants in 3D spaces. Alright, so let's see if we can have those pictures here. Yeah, so this is your uh, let's say this is your normal 3D space. Alright, so this is your I cap, J cap, K cap in the normal position, and after the linear transformation you have uh, you have a transformation like, let's say, this one. Okay, so after the linear transformation, your area, I'm sorry I cannot like show you in a proper way, but this is better than nothing actually. So this was your this was your um, initial condition, and after the linear transformation, means after multiplying with a uh, particular matrix, your vectors become like this. The vectors becomes like this. The vectors become like this. So this particular shape is called uh, parallelepiped. Alright. So whenever your volume is stretched or squished into something else in 3D, that particular shape is called a parallelepiped. Right. So this is difficult to uh, draw in the workspace or white space. So that's why I have captured these photos. So um, so yeah. So this is all about the determinants in 3D spaces. So whenever you have a matrix and you have linear transformation, so um, from this particular initial position, you comes your transformation becomes a parallelepiped, and the determinant actually says that how much the volume has changed. That means how much the volume has stretched out or squished in the 3D space. All right. So the negative determinant and um, the zero determinants work same as the idea of the 2D conventions, right? So a negative determinants has a lot to do with the orientation in 3D spaces, and a zero determinant actually means you have squished a plane onto a line, or you have squished a 3D plane onto a 2D plane or a line, or maybe sometimes on a single point, right? So whenever from a plane you come to a line or a single point, your determinant becomes zero. All right. Now, so um, this is the underlying idea or the basic ideas of the determinants. So I hope you're all clear about this. Now let's see some properties of the determinants. All right. So the determinants has major three properties. So um, so the properties of determinants. Now, the first three properties are the major three properties. All right. Um, so we have a total of 10 properties, but the last seven properties um, are actually or can be derived from the first three properties. All right. So our first property is the determinant of an identity matrix is 1. So I hope you all know about identity matrices. So this is an identity matrix in 2D space. This is an identity matrix in 3D space, right? So this all has a determinant of 1. So this is our first property. All right. Our second property is exchanging exchanging any any two rows of a matrix reverse the sign of the determinant. So previously we saw in the first property that the determinant of an identity matrix is 1, right? So do you know about permutation matrices? So in the permutation matrices, we actually change the rows of the identity matrix, right? So the determinant so what should be the determinant of a permutation matrix? So the determinant of a permutation matrix would be in fact 1 or a negative 1. Why? Because if you change any two rows of a permutation matrix, sorry, so if you change any two rows of an identity matrix, the determinant will be a negative 1. But if you change again the rows of a permutation matrix, the determinant or the sign of the determinant will be again reversed, and a negative 1 would be transformed into a positive 1, right? So let's see an example. So let for this, let's say you have initially this identity matrix, and from this matrix you come to this 0 1 0 1 0 0 0 0 1. So the determinant of this particular permutation matrix is a negative one because you have changed the first and the second rows, right? Now again, if you change the rows, let's say the second and the third rows, then the determinant of this particular permutation matrix would be a positive one. So if you multiply a negative one with this negative one, you get this positive one. It's very easy, right? So the determinant of a permutation matrix might be 1 or a negative 1. So our property 3 is all about linear combinations. Is all about linear combinations. So it can be divided into two parts. So the first part is, let's say this is our 3a. Sorry, this is a 3a. So our 3a says that uh, multiplying any row of a matrix by a scalar factor has the following effect. So let's say you have a matrix A, B, C, D. So what is the okay? So you have this particular matrix, and you have multiplied the first row by T. So you have T A, T B, C D. So you have only multiplied the first row with the scalar factor T, right? So the determinant of this particular matrix or this particular thing would be T into the determinant of A, B, C, D. So that this T comes out. Alright. So if this particular matrix, this one, has a determinant AD minus BC, then the determinant of this thing or this uh, uh, multiplied factored matrix would be T into AD minus BC. So this is our 3A, and our 3B is uh, adding something with a row. So adding something with a row has um, the following effect. The following effect. So, suppose you have added something with the first row, a prime plus, there comes a b This B prime, this is C, and this is D. So the determinant of this thing would be same as A, B, C, D plus, sorry, um, so I forgot to tell you about the notation, which I'll be telling in a second. So A prime, B prime, C, D. So the determinant of this thing would be equal to determinant of this thing plus the determinant of this thing. Alright. Now, what are these two bar signs? So whenever you have this third bracket A, B, C, D, it means a matrix, right? And whenever we have two bars, it means the determinant of that matrix. Alright. So I hope you all know this. This is our first three major properties of the determinants. Alright. Now all the other properties um, actually derived from these three properties. Okay. Now let me clarify on one thing, that this is a linearity, right? But this so this is a linearity, right? But this linearity is only applicable for the rows. All right. So it doesn't or it cannot be applied on the whole matrix. Means I cannot write it like this, that the determinant of A plus B is equal to the determinant of A plus determinant of B. No, this is completely wrong. Alright, so the determinant is not it doesn't work linearly. Alright, so uh, it cannot has the same effect as the rows. Alright, so the linearity only is only true for the rows. Alright, so let's see some other properties. So property 4. So the property 4 is if when any two rows are equal, then the determinant is actually 0. Okay. So for reasoning of this property 4, you can use property 2. Okay. So the property 2 was uh, what was the property 2? So sorry, our property 2 was uh, exchanging any two rows of a matrix reverse the sign of the determinant, right? Now think about this one. So the sign did change, right? So if you exchange the two rows, so let's say you have a matrix A, which is in fact A, B, C, A, B, C, D, E, F. Alright. So the two rows of this particular matrix are equal. So if you so let's say this has a determinant, let's say C prime. Now if we have a C there, so let's say this is X. This is X. Now if you exchange these two rows, what would be the effect on this matrix? Actually nothing. DEF. So according to the rule 2, the sign of the determinant must be reversed, right? So it should be like a negative X. But you said that this matrix has a determinant of X and this the following matrix is in fact the same matrix. So these two matrices are actually the same matrices, right? So it cannot have a negative sign here, but it can have a negative sign here, but the effect should not be visible. So what is the value where the positive and negative signs doesn't actually matter? We all know that is actually zero, right? So whenever this particular value x has a value 0, then negative 0 or positive 0 doesn't really matter, right? So in this manner you can actually do the reasoning to the property 4. So I hope this this idea clears out your conception of any two rows being equal, the determinant is 0, right? Alright, so our next property is property 5 is while the elimination, the Gauss-Jordan elimination. So while mm, the elimination, while elimination, if any particular scalar L into row I is subtracted from any row, let's say row K, so the determinant doesn't change. So you can also prove this property. So let's say you have an initial matrix A, B, C, D. Now in any point of sorry, now in any point of uh, elimination, let's say you have done this thing A, B, C. So you have multiplied L with row 1 and you have subtracted that um, that thing or that L into row 1 from the second row. So you have this effect on this matrix B minus, sorry, it should be D here. So D minus LB. So from the 3B rule, we can write this the determinant of this matrix as A, B, C, D plus we can have A, B minus L, A minus L, B. So we can actually we can actually like take out the L here and oh, okay, so let's take out the negative L. So minus M and A, B, A, B. Alright, but uh, in the previous property we saw, so in property 4, so in this property we saw that if any two rows are equal, then the determinant is 0. So the determinant of this particular matrix would be 0 because the rows are equal, right? So we can say that the determinant of this thing would be in fact A, B, C, D. So your determinant doesn't change in this case. So our property 5 is proved. Right. So let's come down to the next property, which is property 6. So this lecture is all about learning the properties of the determinant, which is a very important part of linear algebra. Right. Okay. So our next property is very easy. A complete row of zeros leads to a determinant which is 0. So this notation means the determinant of A. Alright. So how is it possible? So let's say you have a matrix T A T B C D. So you can take out the T outside of the matrix. So A B C D. So if you have T equals to 0, so if you have T equals to 0, then um, what would be the determinant of this matrix? The determinant of this matrix would be 0, right? So put the values of T here. So 0 0 C D. So if you have, so this might not be a very suitable example, but you get the idea that if you have a complete row of zeros in any part of the matrix, so that leads to the determinant of the matrix to 0. Right. So our next property is, so you know about upper triangular matrices and lower triangular matrices, right? So in the upper triangular matrices, uh, in the uh, in the in the diagonal we had all the pivot values, right? And in the lower triangular matrices we had ones, right? Like a bunch of ones in the diagonals. So for any, so this is a property 7. So for any lower, let's say not lower, because the lower triangular matrix will have a determinant of 1. So for any upper triangular matrix, the determinant is the product of the diagonal elements. Okay. So suppose you have uh, a triangular matrix as this d1, d2, d3. So you have some values here, some values here, which are non-zeros, some values here, and you have zeros here. Okay. So the determinant of this matrix would be d1 into d2 into d3. Alright. So uh, so what should be the reasoning? The reasoning can be, so let's say you have And let's say you have the u, which is this one, so d1, d2, d3, and we have these values here. Sorry, this thing should be 0, right? For any upper triangular matrix, there should be zeros there. 0, 0, 0. Now from this matrix, you can actually, so in the row echelon form, you could, after some elimination, you could make these entries 0, right? You could make these entries 0. So d1, d2, d3. So after some elimination, so um, you multiply something with d3 and you subtract it from this part or this element and it becomes 0, right? You multiply something with d3 and subtract it from this um, 1 3 element and it becomes 0. Similarly, you can get 0 here, and these there were zeros here from the initials. So from this matrix, you can take out d1 from the first column, d2 from the second column, and d3 from the third column, and you'll have a matrix like this: 1 0 0 0 1 0 0 0 1. And from the very first property, we know that that the determinant of any identity matrix, so this is the identity matrix, is 1, right? So the determinant would be d1 into d2 into d3 into 1. So yeah, so this proves that for any upper triangular matrix, the determinant is the product of the diagonal elements. Alright, so this is the property 7. This is a very important property. And um, the eighth property is uh, combining combining the sixth property and sorry combining the sixth and the seventh property, we can say that the determinant of a would be 0 when a is singular. Why? Because whenever a is singular, that means it will not have a pivot in any particular row, right, or any particular column. So a whole row of that matrix which is not singular would be 0, right? And whenever a whole row of a particular matrix becomes 0, then the determinant of that matrix would be 0, right? So the determinant of any particular matrix A which is singular would be 0. And the inverse is also true. So the determinant of A is not 0 when A is invertible. So okay, that means you have a pivot in every column of that matrix. So none of the rows are actually 0 in this invertible case. Alright. So these are two important properties that if ever you get a singular matrix, then the determinant of that particular matrix would be 0, and if it is an invertible matrix, the determinant will not be a 0. Alright. So let's see a short example that how we can find the determinant of any matrix. So let's say, sorry, uh, let's say our matrix A is equals to A, B, C, D. Alright. So if you try to perform elimination on this matrix, so if you try to perform elimination on this matrix, what will you get? So we multiply mm, we multiply the upper row by C by A, this first row by C by A. So and then you subtract it from the second row, right? So let's do it. A, B, C into, sorry, C minus C by A into A, and B minus, where a D here, sorry. So B minus uh, the first D minus the first row divided by D into this this C comes here, right? Is it really the case? What do you do in case of elimination? So you multiply something with the first row and then you subtract it from the second row, right? Yeah. So I think it is right. So you multiply the first row by by an A, and then you multiply, you're subtracting it from the second row. I think it is alright. So this will have 0 in this case, and the overall effect will be AB 0. Then I think I made a mistake here in this case. So it should be D minus uh, it, the C by A into D. Yeah, I think it's okay now. Yeah, you multiply something which in this case is 1 by A with the first row and then subtract it from the second row, right? So in this case it would be like D minus C by A into B. Okay, so what would be the determinant of this matrix? So we know that if you have an upper triangular matrix, which in this case is true, this is an upper triangular matrix U, so you multiply the diagonals, right? So the diagonals are A and D minus C by A into B. So in this case, the result is AD minus BC. This is the determinant of this particular matrix A. Right? So this is the determinant of A. So if you have any matrix, you uh, the easy way to find the determinant of that particular matrix is you find the upper triangular matrix. You find the upper triangular matrix from that particular matrix by Gauss-Jordan elimination, and then you multiply all the elements of the diagonals. That's how you find the uh, determinant of any particular matrix. So this is our last two properties, property 9. So property 9 is very handy, like determinant of AB is equals to determinant of A into determinant of B. But as I told earlier, determinant of A plus B is not equals to determinant of A into determinant of B. Alright, okay, so uh, from this property we can actually find out like what is the determinant determinant of any inverse matrix. So inverse means uh, any inverse matrix or the inverse of any matrix A. Alright. Okay. So we know that A inverse is actually I. Right. So if you multiply any matrix with its inverse matrix, you get the identity matrix, right? So if you take the determinant of the both parts, you have this line. So from the property 9, you can say that the determinant of A into determinant of A inverse, sorry, the determinant of A and the determinant of A inverse equals to, what is the determinant of an identity matrix? This is 1, right? So the determinant of any inverse matrix is 1 over the determinant of the initial matrix A. Alright, but A has to be invertible. A has to be invertible. Alright, because if A is not invertible, then the determinant of A has a value of 0. So 1 by 0 is like has no meaning, right? So A has to be invertible in this case, and the determinant of any inverse matrix is 1 over uh, the determinant of the initial matrix A, or the uh, yeah, or the particular matrix A. So if I give you a matrix, let's say A 1 2 3 4 5 6, let's say 11 12 13, okay, 11 22 33. No, this is a bad example. Alright, so if you have a matrix, let's say 1 2 and 6 11, a 2 by 2 example. So if I give you this matrix and tell you to find out the determinant of the inverse of this matrix, it is very easy. You find the determinant of this matrix, which in this case is 11 minus 12, so which is minus 1. So the determinant would be 1 divided by the determinant of A, which would be also a negative one because 1 over minus 1 is a minus 1, right? Okay. So uh, a question, a homework. Our homework is you have to find out what is determinant of sorry, what is the determinant of a square, and what is the determinant of 2a. So this 2a means we have multiplied 2 with every entry of that matrix A. Alright, so this is not a linear operation. Alright, so in our previous cases we multiplied only a particular row by any scalar factor 2 or any other scalar factor. But in this 2a, keep in mind that all the entries of this particular matrix A is multiplied by these 2. Alright. So what would be the determinant of this in this case? So try to find out in your homework. So uh, in the next handwritten note, solve these two at the end of your handout. Right. So with this we come to our last property, which is determinant of A transpose is equal to the determinant of A. So how can we do it? So as you all know that any matrix A can be formed into LU, right? So lower triangular matrix into upper triangular matrix. Okay. So the determinant of LU is, according to rule 9, is the determinant of L into determinant of U. Okay. So do you know what is in the diagonals of the lower triangular matrix? Okay, you can always look back and check that the diagonals of this lower triangular matrix or any lower triangular matrix is 1. So the determinant of the lower triangular matrix would be the product of the elements of the diagonals, right? So as there are all ones there, so the determinant of L should be 1, and the determinant of U is, let's say, x. So the determinant is x here. So so what do we get in this case? So the determinant of A is x. Alright. And if you have transpose, so A equals to LU, right? So what is A transpose? A transpose is in fact U transpose into L transpose. So the determinant of A transpose is equals to determinant of U transpose into determinant of L transpose according to the rule 9. Okay, so uh, determinant of the U transpose into, so determinant of L transpose. So as I said that the diagonals of a lower triangular matrix is 1. So if you transpose that matrix, the diagonal would be same. The diagonal elements will be same, right? Once. So you have 1. And also in this case, the determinant of U transpose. So let's say you have this D1, D2, let's say something here, and and 0 here. So if you transpose this upper triangular matrix, if you transpose this upper triangular matrix, the diagonal elements would not be changed, right? Only the position would be changed, maybe. Not in this case, but in a 3 by 3 example. So let's have a 3 by 3 example. So we have d1, d2, d3. Some elements here. We have all zeros here. Alright. So if you transpose this matrix, the d1, d0, 0, uh, d0, d2, uh, sorry, there should be an element here. Some element d2, d0, in some element d3. So as you can see, the diagonals actually never change in case of upper triangular matrices. Upper triangular matrices, right? So the diagonals remains the same. So if you multiply the diagonals, you have the same x. Alright. So in this case, the product of the diagonal is also x. So x into 1. So this comes to x. So this is the determinant of A transpose, which is also x, right? So in conclusion, you can say that the determinant of A is in fact equals to the determinant of A transpose. Yeah. So these these are the 10 properties of determinants which are very essential for like learning the next few lessons. We have only a few lessons left in our course because we only have maybe 2 or 3 weeks left. So try to cover uh, how to find out the determinants, the Cramer's rules, and the eigenvalue and eigenvectors. All right. So maybe there are a lot of mistakes in this lecture. I made a lot of fumbling, so I beg a pardon for that, and hope to see you in the next lecture, inshallah. So, Assalamu alaikum.